to neutralize acids, which was actually the basis for identification of this mineral based on another Phoenix instrument, the MECA instrument. Mike?
Thank you, Bill. MECA is a suite of instruments that includes 4 wet chemistry cells, it includes 2 microscopes, and it includes a conductivity probe at the end of the robotic arm. We've been enjoying a feast of data from these instruments for the last 4 months. I'll tell you a little bit about all 3, including additional evidence for the 2 materials that Bill Boynton just told you about. So let's start with the chemistry. Now, one of the first findings we announced at the beginning of the mission was the pH of the soil, which we now believe is about 8.3. That's a little lower than we initially thought in our first preliminary report. That turns out to be almost exactly the pH of ocean water on Earth. And ocean water is that pH because it is held there by a lot of undissolved calcium carbonate by a process we call buffering. One of the ways you know you have a buffered solution is when you add acid, which we do in the MECA experiment, the pH doesn't change very much. And so we saw exactly that response, suggestive of carbonate. And the way we know it's calcium carbonate is that there should be a certain amount of calcium in the solution, a certain concentration, to go with calcium carbonate. And we see exactly that concentration. So indeed, using 2 entirely different methods, the thermal method from TIGA and the solution chemistry method from MECA, we have confirmed the presence of calcium carbonate. And if you combine that with our previous discovery of perchlorate salts in the soil, we really now have enough information between carbonates and perchlorates to begin rewriting the book of Martian geochemistry. Now let me transition over to the optical microscope. When you look at sand on a beach, you see a sea of whitish stuff, and it's not until you look up close under a magnifying glass or under a microscope that you really see all the different mineral grains and types and sizes and shapes and colors that really make it so interesting and tell you about the mineralogy of Earth. The same is very much true on Mars. And I can say we've finally gotten to the bottom of the pile. We finally see what all these really tiny particles look like, what they're made of, what kind of shapes and crystalline forms they have. So we'll start by looking at the first image, which is what we call a through-focus reconstruction. It means we've taken a bunch of images at different focus positions and combined them to make them look like one in-focus image. Now, most of what you see is this reddish orangey, this rust-colored fine powder that we tend to call nanophase iron oxide because that sounds better than rust-colored fine powder. And in between that, you see all these little darker and lighter, larger particles. I say larger, they're smaller than the width of a human hair, but compared to the fine stuff, these are relatively large. They come in all colors. When you look at these images as they're released on the website in coming weeks, you'll see them in really their full glory, as you see in the second graphic. And you'll find that these are clear, these are red, these are green, these are dark. And in particular, the reason in the second graphic that they're all clustered like that is because they're strongly magnetic. You're looking at the surface of a magnet. All the fine red stuff has fallen off the magnet, leaving behind all these little Easter eggs of all different colors and shapes. Now, in addition to these rounded particles, which we believe are rounded because they've been tumbled by the wind across the sand and they've been polished, you also see a lot of angular particles that are clear, that are very white, as if they're salts, that are in different colors. So we can start to see the different animals in the zoo of Martian mineralogy. That still leaves this red nanophase iron oxide to understand. The particles are too small to see with our optical microscope. They're actually smaller than the wavelength of the light that we're looking at. So fortunately, we have an atomic force microscope that can bring back images of particles much smaller than even a pixel on the optical microscope. And it does that by feeling the surface of those particles with a very fine machine silicon tip. And when we start looking with the atomic force microscope, it's a very difficult process. We have to find the particles first, but we've managed to capture a few dozen like the one in the first graphic. And what most of these have in common if we could bring up that graphic, please, is the fact that in the upper left, you see it's flat and smooth on the top. It has a sharp point. It has a sharp angle. And we see lots of different combinations of these. Sometimes they're stacked up. Sometimes they're different angles. They're often standing on end. But they remind us of what we look at when we see these, what Bill referred to as these sheet silicates or phyllosilicates. There's an example of the phyllosilicate in the lower right that was taken by the Clay Mineral Society on Earth, and that happens to be a denticulated pyroxene. But this family of silicates is not dissimilar to what we're looking at with the atomic force microscope. So what we have to talk to you about with microscopy in coming weeks will be this accumulating kind of a library, this catalog of different types of particles and crystals and salts and hopefully silicates. Now finally, let me talk a little bit about the TECP. It's at the end of the robot arm. We've been busy sticking the needles into soil in different places, looking for signs of ice, signs for liquid water, almost liquid water, water vapor. Now the interesting result here is that we didn't find very much. Why is that interesting? Well, no dampness, no traces of not quite frozen water, not even the humidity in the air above the soil that you might expect just to rise from the warming ice. So in other words, what we've learned from the TECP is that the soil in our little corner of Mars is very, very dry. And with that, I'd like to turn the microphone back to NASA headquarters in Washington. Thank you.
Okay, thank you. So for the past 4 months, we've been continuously monitoring the weather at the Phoenix site. So this has included standard meteorological measurements of temperature, pressure, and wind. We've been taking images of the atmosphere. We've been coordinating these measurements with observations from orbit as much as possible. And we also have an experimental instrument called a LiDAR, which has provided a view of the atmosphere that has never been seen before. And I'll start with just the temperature measured over the mission. So the graph on the screen is showing the minimum daily temperature from Sol 0 landing day up until about Sol 120. And you can see that for the first 2 months of the mission, the temperature was increasing. The summer solstice was at about Sol 30, and then the temperature started to decrease. And now while the temperature is decreasing, we have observed water condensing in the atmosphere. So over the first 2 months of the mission, the humidity of the atmosphere was increasing as water sublimated from the ground in the polar ice cap. And over the second half of the mission, we started to see frost, ground fog, and clouds. And this is now occurring every night. Okay, so the next screen shows images of of clouds drifting past the horizon. If we could see the next screen, please. Okay, so this is the view out over the horizon just about every morning now. So this is in the early hours of the morning, and we see that there are clouds drifting by on the horizon. So this is where the LiDAR comes in. So the LiDAR is able to probe the inner structure of the clouds. So the LiDAR instrument emits pulses of light upward into the atmosphere and detects what is scattered back. Now this image shows, first of all, on the right, a graphical depiction of the LiDAR, the laser beam pointed upward from the lander. So at the heart of the LiDAR is a laser. It emits pulses of light 100 times per second. And if you were standing beside the lander looking upward, you would see a continuous green beam. And that is what we're seeing on the left side of this image. That's a picture taken with the SSI camera. And it's actually been, we can go back again. Sorry, okay, so that green beam is a series of images from the SSI camera. And you can see bright spots in the beam, which are actually ice crystals, laser light reflecting from ice crystals. And at the top of the beam, it's brighter because it's reflecting from a cloud, which is a few miles above the surface there. Okay, so in the next image,